So they're calling their L1 PLC1 and PCL2. So odds are when you get out there, they're not going to call them L1 and L2. They're going to call them whatever they call them. But usually they'll have L1 and L2 in the designator for the two lines. These are line numbers on the left. These are cross-reference numbers on the right. So notice we don't look, this would be a rung, and this would be a parallel circuit, right? I say that because we have multiple loads or multiple coils, but they're in their own line, right? Makes sense? Every line that lines up horizontally gets the same number. So this is line number 137, which is the page number on the drawing. Line number 2. Notice the line started what? 0, 1, 2, 3, 4, 5. So they're numbered sequentially right down the page. So this coil right here, they're calling, so this is the name of this coil, 5B1DB. So they give coils names. And usually they're going to be some type of mnemonic, some type of memory jog. So you can come in and get a good idea of what it does. And after you look at it, and they put comments over here, by the way, where you can actually see what the mnemonic stands for. So this is line number what? 1. And then it says this guy here has a normally open contact somewhere in line what? 2. Y'all understand that? So how do I find it? Well, your contacts are going to have the same name as your coils. Does that make sense? Okay, and this will also be true. I can show you later on where you can name your coils, and then you can name the contacts will take the same name. I'll show you. So here's line 2 right here. So here's line 2, and I'm looking for what? 5B1DD. Here's line 2, 5B1DD. There it is. Okay. Make sense? If it's underlined, it means that we would be looking for a normally closed contact. But we can't see it because it's in line 57, and we don't have line 57 on the drawing. So we separate the contacts with a comma. So this is the location of the what? The contacts that are being controlled by this relay. That makes sense? Everybody okay? Any question? This is motor control. Now these are wire numbers, so we'll get the wire numbers when we get into the tag mode. So this time it's like a word. So these are what? C, everything under C is what? Line number. Everything under A is what we call cross-reference. Everybody okay? So the guy kind of gets out of whack when he does what's going on here. In the drawing in the book, he didn't do the line numbers. So I can show you all type of motor controller relay logic that would show that. What rule was we on? Oh yeah, the location of each relay contact controlled by a coil is identified by writing the line number, the contact location to the right of what? L2. So cross-reference numbers are on the right of L2. Line numbers are on the left of L1. Everybody okay? And then that's the last rule. So it's 10 rules. The guy came up with 9 rules, but he kind of messed them up. Are we okay? So what we're going to do now is in the next chapter is get into rules for PLC programs in ladder language. Now, there's almost no PLC that I know of except Mr. Foster over there told me about an ABB PLC that didn't support ladder logic. That's the only one I ever heard of. Since they've changed. But he said the new version comes out to supports it. So that's the language we're going to teach, even though there's several languages. Rule number 1, it says input instructions must be input instructions. Right? You'll understand. So these are going to be instructions. So everything we put in a PLC program is an instruction. We have input instructions, we have output instructions. And we have different input instructions and we have different output instructions. So input instructions go on the left, right? You understand? Between L1 and the output instruction. So the output instruction is going to be on the right, connected to L2, right? You understand? The input instructions are going to be on the left. And they may or may not be connected to L1, because they might go through another input instruction. So we can put input instructions in series, we can put them in parallel, we can put them in series parallel. We can only have one output instruction per line, but we can have multiple lines on your output. So we can have parallel circuits, right? You understand? We can't have what? Series circuits or series parallels. So all our input instructions are going to go toward between L1 and the load, and then our output instructions are going to be between L2 and the input instruction. That makes sense? Everybody okay? If you don't hook it up right, then what are you going to get? You're going to get an error. Because this is a computer. A computer looks for syntax, the correct way things are drawn, right, or written. So if you put something in the wrong syntax, then you're going to get an error. Rule number 2, output device instructions are placed between the rungs control devices and L2, which is the right vertical line, right, or the right vertical rail. Nothing is allowed between the rung output instruction and L2. Nothing. So we don't have overloads inside a PLC. If we use the output of the PLC to control a motor starter, then the overloads would be on the outside of the PLC. Everybody okay? If you do this wrong, what's going to happen? You're going to get an error. Rule 3, all instructions must be placed horizontally. This is done what? Automatic. It's a computer. It's going to take care of it. So it won't let you put, a PLC will not let you put anything horizontal. Vertical. Continue on back. A rung's output instruction must not be placed in series with another output instruction. Multiple rung output instructions can only be placed in parallel in another what? Line. But in PLCs, we don't number the lines, we number the rungs. Everybody okay? If you do this wrong, then you're going to get a what? You're going to get an error until it's corrected. So over here on motor controls, you're wiring it up with wires. If you wire it up wrong, then you screwed up. A lot of times on your PLC, it's a computer, right? You understand? You're writing a program. And if you put something in the wrong syntax, not in the correct order, odds are it's going to give you what? An error. But that's what you look at and you say, well, what my error is? Oh, I put 2 outputs on one run. Rule 7, this is automatic, Rule 6, all rung numbers are automatically placed on the left side of each rung when you insert them. So rung numbers are numbered for. So you don't have to, the book says all have to be there, but I've never seen, by the way, Siemens don't call them rungs, they call them networks. So that's a kind of little difference too. But the network numbers are put in automatically every time you create a what? You create a new network. Now, why they don't call it rung, I don't know. But comments should be added to each instruction symbol or and rung. And then number 9, this is user defined. So 8 is user defined, 7 is user defined. What did 7 say? Did I skip over that? Each input and output device instruction's logical address is entered above each device's symbol. The output is predefined by the Ladder Logic PLC program and application. So when we see on this one, we'll enter it on above, and it'll put the first part of the instruction on top, and then it'll put the bit number on the bottom. We'll have to show you all that, and it'll make sense. Okay. Where we at? Number 9. Everybody okay on that? Comments. Why we use comments, and I'll show you some of RS Logic's. I'll show you all the programs that actually run the manufacturing line. So you write a program that's got 150 lines of code, and you need to come back and edit that thing. You don't put any comments or anything in there. So you don't know what this rung does or what this guy here does. So comments are pretty important. So we'll show you how to put comments and stuff in there. Each instruction symbol should be given a name that relates to the instruction function in the control circuit. Siemens requires it. Allen Bradley, this is option, but we're going to make sure we do. We'll do rule number 9, and we'll show you how to do that. So what you're going to do is you're going to give a symbol a name. And what's nice about giving a symbol a name is that you can use the name instead of the address from then on, which makes it really, really fast. Are we okay? Any questions? So let's look at the PowerPoints. I think this is 5, so that might be 6. So after we get through with this guy, we're going to start working with PLCs. So we're going to move down. Our PLC lab is down in Lab 200, and that's where we going in. So we okay so far? So sure are quiet. Good gracious. List of rules for creating PLC ladder diagrams. That's the rules. The guy's got problems. Convert a relay logic diagram to a PLC ladder logic diagram. Create a ladder logic diagram when a PLC is in offline mode. Download the PLC ladder logic diagram and test them as on a trainer. I guess it should be test it, because you can unlike computers, these guys are made to run control diagrams. They don't multitask. They run one program. You have one program in that PLC at a time. You can split the program up into subroutines. We'll talk about that. But we're not going to have more. So you're going to either upload the program, download it, upload it from the PLC into your computer, or download it into the PLC. Now that's backwards from the internet, right? You understand? So we download it to the PLC, we upload it from the PLC into the memory. So we can take a program that's inside the PLC and we can upload it back into our programming application, or we can take a program and then we can modify it and do then download it back into the PLC. Download a PLC ladder diagram and test them on a trainer. We're not going to do that tonight, but we'll get into the lab hopefully next week. I use force instructions for troubleshooting, but I've already showed y'all that. It's pretty simple on this one. Create and print reports. We're not going to do that. We're going to say, because we don't have printers over there, save and open ladder logic project files. This is a really, 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 really simple ladder logic diagram. Except we broke some rules. The ladder logic is the dot over here indicating everything. So we have a normally open push button. By the way, the symbol for a normally open push button is usually up here. For some reason, it's right on the top. It makes it a little hard to see. So we have 2 normally open push buttons. Then we have what we call a normally open limit switch. So that limit switch is like that guy I was showing you over there. So when that carriage come over here and hit that operator, it would make the switch. So those are mechanically, those are contacts. Huh? The E-stop could be out anywhere. It's not in this ladder diagram. So usually the E-stop circuit is not in the ladder diagram, very seldom, and it's never in a PLC ladder diagram. You have an instruction that you could use to turn off the outputs, and we don't use that in this class. We'll use it in PLC too, but the E-stops are not shown. Now, we can look at US Steels and there's no E-stop up there, even though there's an E-stop in the circuit. That makes sense. Now this would be the same program in PLCs. In Allen Bradley, the addressing for the logical addressing for Siemens is a little different. So what we would do is we will come in here and we can put this program in our field. I don't think I got it running. I don't see it. So we're using yeah, it is. So this is a program in PLC. And what I've done here is this is the name right here. These don't have names. So I'm calling this guy input 1 and I'm calling this guy input 2. What Allen Bradley does, it puts the model number under right here. So the way Allen Bradley addresses is we start off with I. So right now we're going to deal with 2 instructions, and we'll switch over later on. So basically, the syntax for we'd start off with I if we're dealing with a what? Input instruction, right? If it's an input that's going to one of our true inputs. So this is the MicroLogic 1100 PLC, and these are my inputs right here. As soon as it focuses in, this is where we establish where it's syncing or sourcing. So my switches are sourcing, so I have my input set up sync. Everybody understand that? Are we okay there? We need to go back over that. That's a very important concept. This has 2 DC commons, so I can set up this set for syncing or sourcing, or I can set up this set for syncing. So this is minus right here, and then I got another minus coming up here, and then here's the inputs. Okay. So each one of these is wired to one of these input switches. These are all input switches. So these are sourcing. These are wired to source. So my inputs have to be wired to sync. Everybody okay there? And what it does, if we can get this thing so y'all can see it, is this guy here doesn't have an LED display. This guy has got a group of, he uses an LCD display. But you can see when I come over here and turn on switch 1, you see it go black right there, indicating that that switch is closed. So these are inputs, guys. So what I'm doing is I'm coming over here, and when I close that, my PLC sees that that input switch is turned on. So it's getting 24 volts DC into port 0. And if I looked at the input table, that input table would have just went to 1 for that reason. Everybody okay? So these are true inputs. So if I say I, then I'm addressing one of these guys right here. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This guy here has 10 inputs. Everybody okay? That makes sense. So over here, when I come up here and put input 0 slash, when I put input, then I put 0 slash 0. And what we're doing is we're addressing this one output, this one input port right there. Everybody okay? Any questions? But we do have other input instructions. It's just they don't go to a port. They don't go to one of our ports. So we'll see later on. But all your input instructions are going to go to the what? To the left, right? Between L1 and your output instruction. And right now we're just going to deal with these true inputs right here. So if I was to come up here and want to address, then what I would do, the syntax is we would put an I for input, one of our input ports, and then we'd put an O for one of our output ports. And these are what we call bit instructions. So we're dealing with a word, so Allen Bradley goes in words. Y'all understand that? So it goes in what? 16 bits. So what we'd be addressing is we're going to say input, and then as soon as I say that, we're addressing a 16-bit input port. Everybody okay so far? So I'm going to come over here and go back to my RS Logic program. Oh, there it is. So over here, and this is in this chapter, this is called the project correct. Everybody okay? And I showed y'all this the other night. So I'm going to come over here and go to my inputs, and I'm going to click on that. See that? So this is the word. That's 16 bits. They're numbered 0 to what? Right, okay, that. And I'm going to come up here and I'm going to change the status of the switch hook to, oh, sorry. It won't show me the status unless I'm in what we call run mode. Can you see what it did? Let me move over here. So here's switch 0, and what did that do? I call bit 0 to go to a what? 1. Then I turned it off, it goes to what? 0. Here's bit 2, here's bit 1, here's bit 0, I'm sorry, here's bit 1. Here's bit 2, here's bit 3, here's bit 4, here's bit 5, here's bit 6, here's bit, and then that's we're out. That's all the input for them. Oh, I'm sorry, no, I'm sorry. Why didn't that work? Something wrong, guys. I gotta figure out what's going on. It's showing up here. We got 10 inputs on here. I'll figure that out later. So what you need to see is that each one of these responds to a bit in a 16-bit word. Okay? You understand that? So in my instruction, I got to be able to tell them which bit are we talking about. So what we do on Allen Bradley is we start off with I, meaning a what? Input. Then what we do on the RS Logic is we put a code. Everybody okay? Then the next thing we would specify would be the module number, or the slot number. This is a fixed PLC. The CPU don't take up a slot, so in a modular PLC, your CPU takes up slot 1, so your first module would be takes up slot 0. Your first module address would be slot 1, right? You understand? This is a fixed PLC. The CPU is integrated, so it means it don't occupy a number, right? You understand? So here we'll start with 0. As long as I don't go past 16. If I go past 16, then we would have to go to the next word. Does that make sense? So that's understood. Then we'll come over here, and this is optional, guys. Then we put a dot, and then we put a word number. So we can buy a 32-bit module. So if I got a 32-bit module in slot, if I got a 32-bit module in slot 2, right? You understand? Then how many words is that? That's 2 words. So I'd say slot 2, word 1, right? You understand? And then after that, we'll come over here, we'll put a slash, and then we'll put a bit, and then we'll put a bit. Now this is the full addressing scheme for Allen Bradley. We don't have any 32-bit modules. So that means this guy right here is gone. So our address is going to be I, and then we'll put the slot number, and then we'll put a slash, and then we'll put the bit number. So this is the what? And this right here is the what? Everybody understand that now? So we don't have any 32-bit modules, but if you get out there and work, they might have bought a 32-bit module, because that's 32 inputs that only occupies 1 slot, right? You understand? But here you would have to say, I'm in slot 1, word 2, right? Sorry, 0 or 1. You only can have 2. Okay. This is a fixed PLC, so all our slot numbers are going to be what? 0. Because We don't have slots in this thing. And then I would, if I wanted to specify that, so this would be the address I would use in the program for input 0. And outputs work the same way. So we'd start off with what? Out. Then we'd come up here, and next would be the what? Slot number. Could be 0, but in a fixed, and if you get one of the 504s, then your output module, your outputs are in slot 2. The inputs are in slot 1, and the outputs are on slot 2. If it's a fixed PLC, it will be 0. So we'll use 0 for this one. But if you was over there on the 504s, you'd say slot 2, right? You understand? It's not a 32-bit module, so I'd come over here and I'd do like this, and that would address the 0 bit in slot 2 for an output module. That makes sense? But this is the true syntax right here. It's the what? It's the type. It's the what? Module number, the word number, slash, and then the bit number. That's the whole syntax there. Can y'all see that, or is it scribbled up? So here they're saying, okay, this would be in slot 0, so this looks like a fixed PLC. And then this right here would be input 0, right? So this would be slot 0, input what? 1. This would be slot 0, input 2. Now this is going to an output port. So it's going to go to output port, and it's going to go to output port 0. 0.0, bit 0, right? Everybody okay? So let's write this program. First RS logic, and this is what you're going to have to do every time. So first thing when you start a new program, we'll go up here. Let's click this thing. We'll go ahead and go offline. Okay. So I'm going to come up here and just say what? File, go what? New. Do you want to close the processor? Yes. And then the first thing it wants to know about me is what is the CPU in this thing? Okay. So these are all model numbers. These are all module numbers. And so when we get into the next class, when I've got one of the 504s, I'll show you where y'all can get this information. What's nice about a fixed PLC is everything's built into it, right? So all I have to do is come up here and go, this is a 1100, right there, MicroLogic 1100. Oops. So picked up the wrong one. Okay. And then it loaded it up. Okay. Now here's our project tree. This is our system files. We can't get into those at all. And this is the default name that they give to what we call ladder 2. So ladder 2 is the main program. In this time, I'll show y'all some true big programs. What we like to do, and they call it structured programming, is we like to take a big program and split it up into individual modules, with each module doing a certain task. And we call those subroutines. So what we do is we have one main program, and then we have a lot of subroutines. And that way, if I need to troubleshoot something, we got a subroutine that does a certain thing, and then all I have to do is go into that subroutine. We don't have time to deal with the subroutines in this class, but I'll show y'all some. But if you take the PLC2 class, and that's one of the things that we do, we'll jump that around. Are we okay? By the way, you can rename it if you want to. So this is a tab. So every one of these ladders, so the default one is ladder 2. That's your main program. So even if you did subroutines, you still have to have what we call a main program that calls your other subroutine. Right now, it gave it the name main program. If you don't like that, you can come up here, just right click on it and choose what? Rename. And I can call it Richard. Notice the tab changed. It did not change ladder 2. So anytime they talk about ladder 2, this is where we're going to be playing around with. They stopped doing this. You can't put anything. It automatically puts it in. So that tells it where it needs to look the program is. So we can't put anything on this one. So the first thing we need to do is insert a rung. So this is our common palette up here. And these are all our other palettes. So here's your bit instructions, your timer instructions. And this is as far as we're going to probably get this semester. Okay? So this is where, so what I did is I've highlighted this and turned it red. And this guy right here, this is where we insert another rung at. And we can drag it. Y'all know how to drag, right? How you drag? Grab it, hold the left mouse button down and move it. And it turns green. See the green X? That says where I can insert the rung. It automatically moved this to rung 1, call this rung 0. So on Allen Bradley, it's like computers. It starts numbering the rungs at what? 0. It says I got an arrow. What kind of arrow I have? Well, I don't have anything out there. So right now it's got a short. So we would come down here. This is a normally open contact. I'm going to come up here, drag it down, see where it turns green. I'm going to drop it in there. Everybody okay? And then what I'm going to do is I'm going to come up. Notice it's got a question mark right there. What's it waiting on?
Dang.
It's waiting on an address. Yeah, it's waiting on a logical address. So I'm going to come here. I'm going to double click on that. And what do we want to assign this? I'm going to say input : 0/0. Oops, slash. We okay? And I'm going to hit return. Now what it's going to do, it's going to ask me for a comment. So we got two things that we can put in. You know, we can say input. You don't have to put a comment. This is optional. Comments are okay. What's really important is this symbol name, and I'll show y'all later on. We'll call it name. So notice the comment is in what? It's in yellow, and the symbol name is in green. The symbol names are what's important. So that's my first instruction. This is an input instruction. It's on the left-hand side. It went there automatically. It wouldn't let me put it on the right-hand side, right? That make sense? So I'm going to come down and drag down another one. I'm going to stick it right there. Y'all see the little X? When I get it in the right place, it turns what? Green. Got it right there. And then we'll call this input 0/1. Hit return. And I'm going to stop with the symbols. Okay, then but look, I entered it. So this is what Allen Bradley does. It puts the word number on top, and then it puts the bit number under the symbol once you enter it in. Then I'm going to drag another one, bring it down, come up here, we'll call this what? Input : 0/2. This is where you have an opportunity to give it a what? Comment. If you don't want to do it here, what you can do is you can come up here and right click it, and then it gives you the ability to do what? And then I'm going to put an output cord. So this is a true output port. And then we'll call that what? Output : 0/0. Then when we get here, notice the arrow stayed on the left-hand side. So this guy right here has got the little computer that's got the check mark on it. You click on that, and if the error clears up, it means you got everything in the right syntax. It don't mean your program's right, but it means you got it in the right syntax. So if I call this input 5 and I meant it to be input 1, it has no idea that you screwed up like that, right? That makes sense? Okay, so I got this program written. That's my first program. Very simple, right? See that? Pretty neat. Then I checked it for syntax. It was okay. And then I'm going to come over here. Right here, it says I'm offline. I'm going to do what? Click on that, and it says, do I want to do what? Download. Here's where we would give it a name. Right now it's untitled, so we could give the program a name. And then we could save it. And then it gave say, what did it say? Then it's going to download the program. The processor types don't match, so it means I got the wrong processor. It's going to change it for me. We're okay. So we'll switch back to. Now, what you notice when we're in the rung mode, both the rails turn green. See that? And when I come over here and make one of my switches, see it indicates that this is true, all right? So what it's looking for, it's looking for this, and switch 1, and switch 2, and then the output goes through.
Did you click off the spare switch?
Huh?
Yeah, when you made all three, the end one.
Yeah, this is the output. So if I was looking at my outputs, of course I don't have anything connected here. And we'll show you how to connect stuff later on. So here's input 0. Here's input 1. Here's input 2. And then output 0 comes. Make sense? And of course, this is AND logic, guys. We're just doing AND logic. AND says all of them have to be true. So if any one of them goes false, notice the output goes false. See that? So this is the first logic. This is what we call AND logic. You can put it in contacts in series like that if you want to. But we'll talk about logic later. That makes sense? So here we didn't have to supply a slot number. Why? Well, we did. It's just that on a fixed PLC, your slot is going to be 0. This is not a fixed PLC. This is a hybrid PLC. So what we can do is we can put another module over here. Your internal would still be 0, and then that module would be what? 1. Everybody understand that? So this is what I call a hybrid PLC. So most PLCs are getting away. You can still get the racks, but a lot of your smaller PLCs, they're going hybrid, so you can expand them if you need to, right? In the old days, like the MicroLogic 1000s that we have over there, those are fixed PLCs, which means what? You get what you pay for. You don't get any more, you don't get any less. So you can't add more outputs to that thing. You can't add more inputs to that thing. You can't add analog to it. You can't add anything to it. You can't change its communication features. This one you can on this one too. This has got two features. We got an Ethernet IP, and then we got the PH485, which is what Allen Bradley uses. I can go get you a brand new compact logic over there, and it's still got the old 485 input on it. So that's something that Allen Bradley's been using for years. Are we okay? So there's our rules. We did what? Rung numbers. How do the rung numbers get up there? Automatically, yeah. So we don't have to worry about rung numbers. How did the contacts get up there? Well, what we do is this is your most often used palette up here. This is a down drop, so if I needed to hook an input, let's go back offline. It won't let us do anything while we're on. Okay, so this is your down drop right here. I'm gonna come up here and bring this down. I got to highlight. So you have to select the rung that you're getting into, and I'm gonna come over and put this down here. And then I'm gonna come up here and I'm gonna drag this guy into there, and then we'll put another now I've shorted that one out. So this is the way we would hook up parallel. So I would come up here, and then I would grab another contact and put it right there. That makes sense? And I'd say input : 0/3.
That's a 4.
That's another, exactly. Now, if I wanted to put another coil over here, then what could I do? I'd come over here, and I'd put a down drop here, and then I'd drag. Everybody okay on drag? What would I do? I'd come up and grab the symbol. I hold my left mouse button, and I would move it here, right, until it turns green. And it pops in there. Now I'm on my right-hand side, so what would I have to do?
I'd have to put another output instruction over there, right? You understand? Now here we're just dealing with coils, but we got several output instructions. So timers and counters, when we get into those are going to be outputs, and they'll always be on the what? On the right. That's exactly. They'll be on the right. But we can put coils in parallel with them, right? Y'all understand that? And then of course, it won't clear up. Now why won't it clear up? Well, I haven't signed this guy right here an address, right? No, I hadn't signed it an address, right? So. And we'll talk about this guy. So I'll assign this is not assigned to an output, because if it was assigned to an output, it would start with what? O, right? That makes sense. Everybody okay? Check it. No, you use whatever you come up with. I'm just doing it for that feature. I mean, I could come over here and call this, I could call this 5 if I wanted to. But it all depends what that guy's giving you. So it could be, by the way, all we have is contacts, but that input port could be controlled by a sensor, right? You understand that? So I could have a position sensor hooked up. The PLC doesn't know what's giving it a 1 and what's giving it a 0. All it does is say, okay, it's either true or false. So all those sensors over there, you notice when I triggered them with my hand, it just turned the light on in front of the PLC, which says, okay, I'm getting 24 volts back from whatever that is, right? So this depends on the logic. So no, we don't go in order. I was just going in order because that's just the way I would do it. But yeah, it could be. We'll look at some of the diagrams over there, and you'll see you'll see an input, this, and then you'll see this, and it'll be all over the place, because you might use the same input. We can use the same input multiple times inside a ladder diagram. Normally, we don't need to use the outputs multiple times, right? You understand that? Inputs, you can use that same address, that logical address. So it says I got an error. Oh, it must be specified to the bit level. So there's some address I didn't specify to the bit level. Notice out here. So by the way, as soon as you get an error, when you check it, this box pops up down here at the bottom. And then it says, okay, it says rung 0. It says error, address must be specified to the bit level. Over here on my B3 coil, you see something messing down there at the bottom?
1762.
No. So what happens when we put in an address, it puts the instruction, it puts the word number or the module number, and then it puts the bit number under the bottom. So even if I enter it up at the top, it puts the bit number on the bottom. It's just, what's missing here? So I'm telling it to use the whole byte. So I'm telling it not a whole byte, I'm telling it to use the whole word. But it's a bit instruction, right? So what can I do? Well, I'll just come back here and double click on this. It opens it back up, and then I can put slash, or I can put anything into it. Okay, now it's got a bit address. Now when I come up and verify it, it says it's good. Okay, so no, we don't have to put them in order. It all depends on how you have your inputs set up. Right? Okay, any questions? So this is our second program. So we'll go ahead and download this. Oops, wrong thing, Rich. Right here, right? And go to what? Download. By the way, every time you change it, it's going to ask for a revision number. You don't have to put it in there. Download the program. It's going to say, the processor's in switch mode. Do we want to switch it to program mode? We're going to say yes. And it's going to ask us, do we want to go back to run mode? And then we'll go online.
So what's it waiting on? Said waiting on input 5. Yeah. See that? Okay. Or I can turn off input 1, and I can do 3, because that's what. I can't read numbers. It's got numbers on here. I was one up. Now you have to understand, it looks like these switches are connected to those lights. All this is programmed, right? You understand that? What I do is I address an input. I decide where I want to use it at, right, in my logic. Are we okay? Okay, cool. And that's basically how easy it is, guys. But the book is kind of rough because the way the lab book is written, it's going to give you a project, something you want to do, and then you're going to have to figure out the program to do it with. Okay, so we'll go back this and we'll go back into the PowerPoint. So slide 0, slide 1, slide 2. This is only going to come into play. This is only going to come into play if you've got a modular PLC or if you've got a hybrid PLC that's got a module on the side, right? You understand that? So if you look at the 1200, the 1214, we've got a module strapped onto the side. Everybody okay? So this is what you have to come up with when you come up with how you wire the PLC. You have to use the symbols that we use in motor controls. So this is a symbol of a normally closed push button. This is a symbol for a normally open push button, but it should be spread out. This is a symbol for a light, and this is a symbol for a small motor. I've never seen that symbol before. Can't be a big motor. I think I told y'all most rule of thumb is the output port on most PLCs weighs around 2 amps. So you can't run a motor, but we can use that 2 amps to pull in a relay, right? And that relay can do what? Can run a motor. So every one of these motors over there run through a relay. So what we do is we start off with a common, which they don't really show it here. So it should be in there like this. So this would be this is 120 volts DC. So it should be in there like that. So this is the way our PLCs are hooked up, is we're using sourcing input. So sourcing means we use plus. This is the common for all our input devices. You understand that? And then the PLC input port would have to be hooked up to the what? Negative. You understand that? And the way I draw it is we draw it in ladder logic. I come over here and this would be my input, and then this would be this would be the circuit for my input port. Well, I got 2 options. I can make that plus or I can make that minus. You understand that? And then I would come over here and all my input devices would still be over here. So this is the common for my input devices. So it's plus, so we say it's what? Sourcing. And then I would have to hook up my PLC port to the minus, so it would have to sync. Everybody understand? That makes sense. But I could have just as well done what? Yes. So I could just as well made that minus and made that plus, if that's what your PLC looks for. Now some PLCs it's built in. You can't change that. On this PLC, we can change them in groups. So on this one, I have a common for this group. So this common would be input 0, 1, 2, and 3, right? And I could put a plus up there. I could put a minus up there. This common right here is for inputs 4, 5, 6, 7, 8, and 9. Now, Alan Bradley is good about that. If you want them to run the same common, you would put a jumper, but I didn't do that because I had two that's available. So this is minus right here, and this is minus right here. So I've got my input set up to sync, my PLC input set up to sync because my input devices are what? Sourcing. Does that make sense? Everybody okay? Now down here, we got a common on every output. So that's a common, that's a common, that's a common, that's a common. So I can control every output, right? And also, these guys here will handle AC. So I can hook up AC, I can use an AC neutral, or I can use a DC common. And we've got one common for every output. So you can see all these black wires under here, what they're doing. Yeah, they're just jumping the commons together because I don't have them separated. You can see this red wire, so that's plus DC, plus 24 volts. So I have, my output ports are set up to source, so my output devices would be connected to the minus, right? That makes sense? Yes, no? So this is the way this PLC is hooked up. So this is the DC power supply. So I have, over here I have the positive pointing toward the PLC. And then I have the negative pointing toward the common for all my output devices. Everybody okay? Yes or no? PLC, the way the PLC does is it constantly scans the program. And what it does, it hits a rung, starts at rung 0, scans the inputs, runs the logic, updates the output. And then it drops down to the next rung. So the more rungs you have, the more scan time it takes. So in the old days, we had big problems because the PLCs or the processors wasn't running fast. And they would literally miss inputs because it was between what? Between scans. It was scanning down here, and I was inputting way up here. And we did some weird stuff. So left to right, top to bottom. Everybody okay? And we can look at the scan time. In fact, I'll show y'all in the program manual for the 1100. It gives you the time every instruction takes. So if you wanted to figure out how long it took to scan the rung, you would just come in and add all those things together, and that would tell you how long it did if you needed to. We're not going to worry about that in this class. Upper scan from instruction, upper left-hand corner, and then starts in the left, right, and works down. Everybody okay? These are your output energized. This is your output instruction. It's actually called an MPD instruction. So that's the technical language. And then we have what we call latching instructions, which I'll show you all. We'll play around with these. Then we have what we call one-shot. Anybody know what a one-shot is? It's not like going out drinking and taking one shot. It's a pulse. So when the input goes true, the output will go, when the input, when the run goes true, the output will go true for a certain amount of time. And we use that, by the way, on that line over there. Input scan, program scan, output scan, are we okay? Any questions here? So what's a scan consist of? It consists of reading inputs, running that logic that we just programmed in, and then doing what? Updating outputs. Everybody okay? Input and output addresses are updated. So that's where it updates. It don't update the address, it updates the table. Right? You'll know that table I showed you that showed you the ones and zeros. Sometimes specific inputs and outputs may not be updated in time. That's what they're talking about. And, we can't look at this. We'll talk about this next semester. We have the ability to set up what we call interrupts, where we've got an input that's very, very important. We can let it interrupt the processor. The analogy I look would be like the way the processors originally came out is the processor would be running a program, And then all y'all guys were inputs or outputs devices. And then what I would do, I'd go to every one of my input and say, do you have anything for me? Do you have anything for me? And you'd say yes or no. And I would scan it like that. And that's basically the way the PLC normally runs. What you find out is an efficient classroom would be, I just go as fast as I need to do, because I know if you have a question, you're going to do what? You should raise your hand. And you interrupt me. That's what we can do that with PLCs. It's just that we're not going to do that in this class. If you take the PLC 2 class, then we'll play around with the interrupts. Project tree. Everybody okay on the project tree? Let's look at the real project tree. Okay, that's the wrong thing, Rich. Where's my Arch Logic program right here? So here's the project tree on the left, right? And this is, we start off with stuff we can't get into. This is where if you had a modular PLC, or this guy right here, or if I snapped another thing on here, right? You understand? Then what I would have to do is this is where I would look at the part number on the module, and then I would add it to the PLC. If you're running a modular PLC, you're going to have to do this. That makes sense? Like I said, I'll show y'all that on the 504s. We don't have access to the system file. Our first program file is ladder 2. Everybody okay? Then we get down to our data files. We get into our outputs, inputs, status, what we call bit files, which is B3 files. Then we get into our timers, counters, then our control register, integer, and floating point. This is where we get into math. What's an integer? Anybody know? Nobody discussed it? An integer is a number without a fraction, so it's a whole number. That's probably what you learned. Then we have what we call floating point numbers. Most people call these real numbers. These are the guys that can have what? Fractions, and the decimal point can move anywhere within the number. We won't deal with these. We do, but we don't deal with it. So when we deal with counters and timers, they only deal with what? Integers. But that's going to be transparent. Okay. This is our force table we looked at the other night, right? Everybody okay there? These are communications. This is where you can come in and you can, no, I didn't want that one. Oh, here's our address and symbol table. So you can actually assign symbols from down here. And a lot of people, before they program, they'll come back and they'll use symbols. Now I'll tell you, let me show y'all the advantage of using symbols. So I'm going to come up here and I'm going to insert a rung right there. Sometimes it'll pop in there on there. And I'm going to come up here and I'm going to type this guy right here. Now, what would it be easier for you to do, to keep up with names of things or to keep up with numbers? Yeah. So notice what I'm going to do here. I'm going to come up here. I'm going to click on that, and I'm going to type in 1. Can y'all see what it did? It automatically inserted the comment and the address for me. So that's the power of symbols.
Because it's copying the same as the one.
Yeah, and so in your new PLCs require you to set up, they don't call them symbols anymore, they call them tags. So your new PLCs basically require symbols. But what you do is you go ahead and assign all these symbols, and from then on you're not dealing with numbers, you're just dealing with what? Names, yeah. So if you don't assign it a name, then you can come down here in the symbol table. Address symbol right here, and we can give it a name down here. I can say add another symbol. And which one don't we have a name for? We'll do output. We haven't done any outputs. And, I used output. 0, make sure I put an O, Rich. I put colon 0, 0/0. And then I'm going to do tab. Oh, sorry. Didn't take. Output colon 0, 0/0. Huh? Oh, right there. I just didn't give it a name. You can give it any name you want to. And then it'll come up here and see it actually. Of course, we still got an error, right? What's wrong with this one? Yeah, it'll come up here and says, what does it say? Output missing. Yeah. Y'all need another break? Okay, so let's take 10 minute break. How are y'all moving around? Y'all know where the drink machines and everything are here? Y'all know where the restrooms are at? Restrooms are down here, first hall to the right. There's some drink machines and snack machines up the stairs.
It's right here. I think that was the day you left there. Probably so.
There should be some more. There's some more over there in the lab. Oh, heck, I got one right here. I got it up. I can run it up. Hold on.
Same one we use for motor controls. Oh yeah, yeah.
You did it.
Yeah. Exact same copy of this thing. Probably like 20 questions. Based on the test, yeah. And they ask you if you want to energize quarter by DJ. Which quarter is not energized? This one has to be energized. This one has to be energized. This one, that one, that. Because all these are parallel to that. So it's a rule. So this one is, you got all the other things. So stop right there. It's all the way there. Stop there. I'm going to go get that. Right on that one. All that stuff on the board and that. We take all those up and yeah, well, I think
you have any more absent then?
So this is the controller. We can't give access to that. We do use IO configuration for modular PLCs, or if we have a hybrid PLC that we put another input-output module on, right? That makes sense. Then this is where we get into our program files. This PLC has the number of program files built into it. So the furthest we can go is up to ladder 15 on this PLC. If you get on the 504, I don't know how far you can go on the 504. Okay. But no making a difference, this ladder 2, this is the one we're going to work in this semester. Everybody okay? And if you take PLC 2, we'll show you how to make subroutines and stuff. Then we get into our data files, guys. These are RAM. This is where we get into these data files. So we have the output data file, the input data file, we have the status data file, then we have the bit binary, which we call the bit file, timers, counters, control registers, integers, and floaters. Each have their own setup data file. Everybody okay? Makes sense so far. And now I showed you all this stuff down here. So let's see what the PowerPoint says about that. We talked about scanning, project tree. So this is called the project tree. By the way, even in Siemens, step 7 and also the TIA portal, they call this the project tree. It's always on the line, on the left. System files, these are reserved. You can't access those. Then we have our main program file, which we call ladder 2, but you can give it a name, but it's still technically called ladder 2, right? Subroutines. So this would be all the subroutines that we could put inside this PLC. So this guy right here, the number of subroutines are fixed. So here's ladder 2, right? These are reserved for high-speed counters, software interrupts. So even if we was going to use these PLCs, they're still data files, but they're specified data files. Does that make sense? So if we was going to do subroutines on this PLC, we would have to start with what? 6. Okay? Make sense? Yeah, let me just clarify. I'm gonna load up the actual programs that's running the manufacturing. That's not what I want. That's the So here's the Pesco line. And here's the distribution station. So this is the first station that's got the Siemens PLC in it. No, this is the actual program. If I click on it, it's gonna, or maybe, nope. Where would that be at? Here we go. So we have PDFs of these. If I double click on that, it would actually open it up. So here's the actual program. And so what they're doing is on this one we got, so right here it says JSR file number 4. So if we went to file number 4, we would see that that would be that subroutine. So that would be ladder 4. Does that make sense? Then this says jump to subroutine ladder 5. And then this would actually be, this is still ladder 2. And here's ladder 3. So there was a subroutine called ladder 3. This is a subroutine. But what they've got is they've got the subroutines actually would have names. You would give it a name, what it does. Of course, you have to understand Festo is a German company. Can y'all read that? So, this is the comment for the rung. We can put comments for the rung. I'll show y'all that too. These are comments for a instruction. So the way we would, if we wanted to, we could put a comment for the rung by. So their subroutines are going to be. So this would be ladder 2, ladder 3, ladder 3, ladder 4, ladder 5, and ladder 6. Right? That makes sense. And each one of these would be subroutines. So your main ladder would call the subroutines. So ladder 2 is still the main one. But if we wanted to give a rung a comment, well, you just come over here and just turn the rung red, and then you right click on it, and down at the bottom is what? Edit comment. And so you could describe what the whole rung does, right? And say okay, and then it would be put yellow above the rung. You can actually put a title for the whole thing. What you would do is you would edit the title. So that would be, you put a title for the whole ladder. Does that make sense? Comments are okay. And comments are pretty important because it makes, if you identify what the rung's supposed to do, then the guy that's coming in, a gal that's coming in troubleshooting, don't have to do what? Don't have to figure out what it does. So yeah, comments are very important. So the book just kind of threw that out, you know, about, oops, sorry guys. I think this is the right PowerPoint. I think it's this guy right. So here's our data files. We have input, we have output, we have status. We've looked at this, a little bit of what these are, right? Everybody okay? Except for B3s. We'll talk about B3s. That's a very important file. This is one of the most complicated, this is one of the harder complex concepts for people in PLCs to understand. And it's very, very important because you'll see this used all over the place. Examine if open, examine if closed. So if I come over and have that symbol, this is a normally open contact. So when would it be true? When it's closed. So this is the symbol for an examine if closed. Okay? Now this is a normally open contact. When would it be true? When it's open. Yeah. So this is our examine if open. Now this doesn't come in, so it's true. So when my input bit goes to a 0, the examine if open would be true. When my input bit goes to a 1, then the examine if closed would be true, right over here. So if I was looking in the bit for that contact, a 1 here would be what? True. And a 0 would be false. Over here, a 0 would be true. And a 1 would be false. You understand that? So people think 1s are always true, not in digital. When you take digital, we can make a 0 just as true as a 1, right? Anybody had digital? Well, if I came up here, so this is a symbol for an AND. 2 input AND. That would be, so here's my inputs. Here ones are true. If I come over and take that and put little bubbles in front of it, what does that mean? That means zeros are true. Zeros are true. So you take digital to find that. Now this gets us into problems. I've only noticed that this really gives us into problems in motor controls. We have a circuit that is probably the most predominant circuit used in PLC. I mean in motor controls. We call this a start-stop station. You'll see these guys here all over the place. Start, stop, start, stop. You can see how this works. We've already looked at this. So we have a button that I'm calling start. This would be L1 and L2, right? Understand that? Now I need a dot right there. So this is a normally closed push button. Okay. So when I close the circuit, then the signal flows from here, right? And then I press this button, what would it do? It's a momentary, that's a symbol for a momentary contact, which means it's a push button, right? You push it, then you let it go. Well, as soon as I push it, it closes and it will come over here and energize the coil. This contact is controlled by that coil. In fact, if I did down here, I might put a 1 and a 2. And over here on this right-hand side, I would put a what? 2. So that means this guy here closes, so the guy literally does what? Seals itself in. Now, how do I stop this thing? Yeah, so out in motor controls, you see a ton of push buttons. And they're big old things, so people can hit stop and start with gloves on, right? You understand that? You don't see very many toggle switches. You see some selector switches, but they'll be big old knobs so they can grab them and turn them with buttons. So I need to start, so I need to turn something on or turn something off, and I want to do it with push buttons. So we have these start-stop stations. And that's the buttons will be labeled start and stop, right? You understand? So this is where people run into problems, because when I program this in a PLC, what we want to do is we want to come over here and do this. Right? And then I would come over here. I shouldn't have drawn that. I don't have a switch. I would hook up a switch to one of my input ports. By the way, Allen Bradley gives their outputs that symbol right there. And this right here would be output colon, let's say 0/3. And then over here, I would assign this to output 0/3. Right? You understand that? Then over here, I would assign this to input of something. 0, 1, 2, 3, 4. So I assign this to input of 0/8. Let's say I assign this to slash colon 0/0/9.
/9,
Yeah. Yeah, we have 10 inputs. So the inputs run from 0 to 9, right? And so 9 will be over here by themselves. And then. Now this is wrong. But the problem is, this is an examine if what? Yeah, sorry. I'm trying to. So this is examine if open. So if I use a normally closed switch, it's going to be false. But the problem is stop buttons have to be normally closed switches. Anybody know why? Somebody never said.
Well, they have to be closed because when you press it, you're breaking the circuit.
But that's not the reason. I mean, we can make this thing work on a PLC, we can make this work perfect with nothing but normally open push buttons. But what would happen, that's my stop circuit. If a wire opens, it's going to open, right? You understand? It's going to open. Well, I'm using a normally open, examine if open, so it's true, right? You understand that? And I couldn't stop my circuit. So if a wire opens, you could go over and you could beat on that push button all day long, and it's not going to do it. It's not going to stop. Okay. So let's look at this. So let's program this in. We're going to program a start-stop station in. Where's my program at? Where's my RS logic at? Over there. I went back. I've inserted a rung up here. Okay. And I wish I had my push button station. All we got is this guy right here. But we've got push buttons on the box. I think it's over near the lab where I could actually disconnect the wire off the stop button. I could sit here and beat on it from now to Wednesday and it wouldn't do what? It wouldn't stop.
Because of the way you program it.
Because of the way I programmed it. I programmed it as one of these. Because this is the way it looks in motor control. Oops, come on. And then we put a down drop, right? And then I'm going to grab this and slide it into there. You need to grab it toward the bottom. And then I'm going to put another contact right here. Everybody follow me so far? And then I'm going to put an output instruction right there. And what I need to do now, I need to assign addresses, right? So we're going to assign this guy here to input colon 0/9. We're going to assign this to input colon 0/8. We'll use one of our outputs that we haven't used. What happened? It's right there. Oh, we've only used one. So we'll use output 3 just for that. Output colon 0/3. And then I'm going to assign this contact to be controlled by that output instruction on
So that when the output through that contact is
there. Technically, it's software. It's not, yeah, but it'll become true. But it's also going to generate an output, so one of my output lights will come on. All right. Now, I could use this contact as many times as I want to. I can only use the coil once, but I can use contacts controlled by that coil as many as I want to. I mean, you can put thousands of them in there controlled by that. A relay, I think I showed y'all that relay. I think it had like, I don't remember, 10 or 15 contacts on it. That's what you got. You know, the PLCs, it's all what? It's all computers. So if it's not a real coil, if it's a software coil, which is what we have here. By the way, I'm not going to assign it to an output. I just thought of that. Now we're going to use this as a start-stop station for everything inside our PLC program. I don't want to sacrifice one of my output coils for doing nothing but preventing this guy from coming in, right? You understand? So what I'm going to do is I'm going to come up here and I'm going to assign this to what we call an internal coil. These are your B3. So your B3, these are control relays. These guys here, their contacts are never going to leave the control program. Guys, we can have hundreds of these things, right? And then I'm going to come down here and change this. I don't know why I deleted the contact. Change this to B3. Now you'll understand B3s. These are coils, but they're internal, right? They never what? They don't sacrifice an output just for a start-stop station. In this PLC, we could put thousands of these things in there. And then what I'm going to do is I'm going to add another contact over here. So what I would do is I would put one of these in all my ladder, right? You understand that? Yeah. Yeah. A B3, a B3 colon 0/0. and we'll check it for errors. So our error looks okay. So what I'm doing is I'm using what we call an internal core. What does that mean? It don't generate an output. So I've only got 6 outputs on this PLC. I got 6 outputs, but I've got a core. I don't need to turn on a light. I don't need to turn on a motor. I don't need to energize a solenoid. It stays inside, the contacts stay inside the control circuit. I don't need the output, right? You understand? So what we use is we use what we call an internal core. We use one of our B3 files. This guy we can put hundreds of them in. I think the 504, you have a B3 and a B10. But it'll show up on the menu over there, right? This one you'd have to add it though. I'll show y'all some. So I could put all kind of coils, but what I would do, if that was my emergency stop, right? So if this is my E-stop, then this would actually be an E-stop button. Now, you can't use software for an E-stop, but you can bring it in. It's just that you would also use the E-stop. What you do on your E-stops is you turn off all your outputs. So what I would do is I would put a contact with a true relay. So true E-stops have to be hardware, which means you got to do what? You got to be able to touch it. But what we would do is this would kill the output software wise, right? You understand? That makes sense. And then what I would do on my PLC is I would put a E-stop contact. Where's my camera? Right there. In this red wire right here. So that's the power. That right there is the power for my outputs. So that would be a true mechanical contact. That would be a relay. So we can't do true E-stops cannot be done with software. Everybody understand that? But normally what we do is we duplicate it inside our PLC, right? You understand that? And then we actually put a true E-stop relay on the output. You can actually see this on the Almatrol. There's a big relay right on the left-hand side of the power supply, and that's the E-stop. So we could use that, or we could use it, or just a standard stop-start station. So to get this thing to work, this guy has to energize, and then after that, all this comes into play, right? But what am I using? Now look right now. What does it say? So let's download this in. So what do I want to use for an E-stop button? I want to use a normally closed push button. Why? That's required. Why? Because if a wire breaks, the motor will stop. Right? You understand that? Yeah. So that's what happens when a wire breaks, it opens. If I use a normally closed contact, then it will open it and cause it to do what? Stop. So I'm using the symbol for examine if open. So let's download this into our PLC. So how do I do that? No file. Right here. Right here, right? Right there. Right there. Then we're going to do what? Download it. It's going to ask me my revision number. You don't have to do that, guys. Then it says we don't have a title on this. It says it's in remote run, so it's got to do what? Switch it over to program. And then it asks me, do I want to go back to run? And then we'll go online. So right now it says the stop button is true, right? So that's this switch right here. And it's actually open. Because I've got an examine if open. So if it's open, it's what? It's true. If I change this to a normally stop push, so this would be like a normally closed push button. Now what does it say? Oops. Okay. This guy don't let you ratchet to it. It says it's what? It says it's false. Because I've got an examine if open. So it means it's true when it's open. If I'm going to use a normally closed push button, I gotta put something that's true when it's closed, right? So what do I gotta use there? And this screws people up on PLCs all the time. By the way, you can change the contact. I'm on top of that. I'm going to come up here and go to right click, if I can remember how to do this. There's somewhere you can change without doing this, guy. Edit symbol. Yeah. And I'm going to change this to an examine if closed. Nope, I didn't want to do that, Rich. What am I doing wrong? Oh, it's change instruction type. I'm sorry. So right now it's a what? Examine if open. I'm going to change it to examine if closed. We'll give this a symbol. I'm going to edit the symbol. We'll call this the stop button. We'll call this the, oops. I want to add, I'm going to edit the symbol. We'll call this the start button. Are we okay? And then we'll come over here and call this guy here. We'll call it run. Notice it automatically assigned the symbol over here. Everybody okay? This will blow somebody in motor control's mind, because in motor controls you have to use a normally closed push button. But here we want to use an examine if closed. People say, let's push the push button. Okay, so I've got it closed, right? You'll see that? I think I showed you that, which is what it's supposed to be. So it's examine if closed, right? You understand? I'm going to come over here and just hit my start button. Now, it didn't generate an output because it's a what? It's an internal coil. Because we don't need an output, right? You understand that? That makes sense. And notice this contact right here closed, and what is it waiting on now? Yeah, so you're waiting on switch 0, or switch 1 or switch 3, and then switch 5. But I can come in any time and hit my stop button, and it did what? Dropped everybody out. So that means this is going to get you backwards, because if you come out of motor controls and you're used to using the symbol for normally closed contact, and you can't use that for a stop button. You can use it for anything else. You just can't use it for a stop button, because the stop button has to be what? Normally closed. So if I break the circuit, then the motor would do what? It would stop, right? Okay. So that's examine if open and examine if closed. So what examine if open does and examine if closed does is, when we look at these output tables, or this input table, is that an examine if open, right? Examine if closed would interpret this one as this one is true, and it would interpret the 0 as what? False. If I use an examine if what? Open, then it would see the 1 is false and a 0 would be true. It don't change the switch. The switch is going to, if it's true, if the switch is closed, it's going to give me a 1. Right? You understand? And that's probably one of the harder things to understand. Besides syncing and sourcing, that's fairly hard to understand. But this examine if open and examine if closed. We okay? So if you're going to use a normally closed input, then you need to put what? An examine if open, right? If you're going to use a normally open input, then you use a what? Examine if closed. Everybody okay? Makes sense? Let's through this chapter and start what we're going to do tonight.
They told me that.
Status host and flag register, we'll look at some of these. Flags. So what we have in computers is we have things that can go wrong, right? You understand? And so what it does is it has, like I do math, and I've got a 16-bit number, and I'm adding it to another 16-bit number. Well, what happens if my sum is greater than 16-bit? Huh? Well, maybe not, but it's got to give us an indication that we had a carry, right? You understand? So we got a carry flag. So a flag is basically inside the processor, and it's looking for what it's checking for. And if it's true, it raises its flag. If it's false, it does what? Lower. So we have an overflow flag. An overflow flag means we've exceeded the range of our signed numbers, and I'll talk a little bit about that. So you got 16 bits for numbers, and you want to do signed numbers. What does that mean? You got to split the 16-bit between positive and negative, right? You understand? So when we look at the N7 files, our positive numbers are limited to 36,767. Our negative numbers are limited to minus 36,768. Now, why do we have one more negative number than we have positive? Zero. Yeah, zero eats up one positive slot. So integers, we're going to be limited down on 16 bits. Well, if I'm doing sign math and my answer changes the sign, right? You understand that? Then we have what we call an overflow. So the most significant bit, when we deal with signed numbers, the most significant bit indicates the sign. So if it's a 1, it means it's a negative number. If it's a 0, it means it's what? Positive. So we sacrifice bit 15, and then that leaves us our other combinations. But you can do sign math where you get a carry into your sign bit. So it would make a negative number flip over to what? A positive, or a positive number flip over to negative. We call that overflow. So if I'm doing sign math, then that would be the bit I would look at. I would look at the status register, and I would see what if we have an overflow. That means the number did what? Change signs. We have so those would be what we call flags. That's just a couple of them inside there, and that's inside the status. Then we have a general purpose for those fixed instructions. That's no problem. That does sign math. So counters are sign. So a counter can count up, or a counter can count down. So we're going to say, okay, it's going to be limited, right? Positive numbers 36,767, negative numbers 36,768. If you exceed that, then that's built into the counter. It'll give you an overflow, right? But we do have some instructions where it don't utilize the internal flag register. So we have another register we call the R6 register, which we won't deal with in this class. So the R6 register we won't deal with. So T4 is used for what? So data file T4 is used for what? Time. We have to give it an address. We have to keep up with a preset. We have to keep up with what we call a multiplier, and all those would be inside the T4 file. But that's transparent to you unless you want to address one of the bits, right? We'll look at that. Counters. So C5, those data files are strictly for what? Counters. The 1100 only supports two types of counters. It supports what we call an up counter and a down counter. And they're weird, guys. They're going to really like that. The Siemens supports up counters, down counters, and up down counters. The Compact Logic, I would imagine, also supports up down. So counters, very important. There's almost no PLC program you won't get into where you're going to run into timers. I mean, even in your car, how many got timers in your car? How many when you turn on your lights open when you turn it off, and after a while it does what? Turns off. Your dome lights will come on, and they'll automatically do what? Dim off. When you park your car, your fan runs for a certain amount of time on your radiator, give it time to cool off. You got a microwave oven, you got a what on it? Timer. You got a rare oven, you got a timer. You got a washing machine, you got a what? Timer. Right. So we run into timers are more predominant than that. Counters, of course, companies always want to keep up with how many they've run, how how many rejects they have, you know, what their input is, what their output is. So we'll get into counters this semester. This R6, this is just general purpose control register. We won't play around with this guy until we get into PLC2. Advanced PLC, we'll talk about this guy. Your shift instructions, your rotate instructions, where we can start manipulating data, which is really neat. So we can make some really neat stuff by just shifting bits around. We can literally take an output and store a pattern in there and then cause it to do a shift. So we can create these lines that move and all this other kind of neat stuff. We're not going to play around with the R6 register here. By the way, this PLC is limited to 0 to 255. That's the number of counters we can put here. We'll never have to do that. Now the actual number, so that's how many RS Logics will let you address. The actual number would depend on what? So it depends on how much RAM you have in your machine. But they will legally address that much. Okay, okay? Everybody okay? So control register R6. Then we have our integer file. This is the one that's limited. So integers are limited between plus 36,767 and a minus 36,768. 32, I'm sorry. I kept saying, I said, that's not right. 32,000. To the 14. To the 15. Your counters are limited by this range. Your up-down counters on these smaller PLCs.
32.
Yes, 32,000. I kept saying 36, and I was saying to myself, that's wrong. That's not the power of 2. So 32,768 is the power of 2, right? Are we okay?
1 second.
Second up. Now, in the real world, if you're using numbers, if you can get by with this range, you want to use integers. If you don't need fractions, if you're using fractions, you got to use a real number, or what Alan Bradley calls a floating point number. But that's what we call a real number. So that's a number that we can put fractions in, right? It also uses scientific notation. So your floating point numbers can use scientific notation. So these numbers can be huge, but you got to understand, the bigger the number, the more memory you're sacrificing, right? And also it does something weird. So if you can get by with this and you don't need fractions, then you'll use your N7 file for your math and everything else. If you're going to deal with fractions, then you'll probably use the floating point. So we get by it real easy with addition, but you got to be real careful with division, because division can cause some fractions, right? So you know, if you're going to get any fractions when you divide, you need to make sure you use a floating point. Here's our B3 files. B3s are these are our bit files. This is what we do for bit addressing. They're primarily, we can use these for other things, but they're primarily used for internal coils. So this is what we in motor controls we call these guys control relays. And they're given that name because their contact never ever leaves the control circuit. So if I've got a relay that don't need to generate an output, right, to the outside world, then I will use one of my B3s. This gives us 255 inside of B3. B10 gives us 256 because we can go up to 255. So that's 512 internal coils we can have. This guy right here, if we got extra memory, we can assign more bit files, and I'll show you that. We can have tons of bit files inside this one, but they'll all start with B. But it might be like B15. So you have to look at the PLC. So the Allen Bradley registers are, I'm sure, this says registers. That shouldn't say that. This guy gets data files confused. These are all what? These are all data files. So Allen Bradley PLCs go in groups of 16 or words. Siemens PLCs goes in groups of 7 or bytes, which is real interesting. And I'll also show y'all some of the PLCs actually have a switch on it. They got a key in there. And you got 3 positions. You have program, which is kind of misleading. That's where you can upload and download programs on it. Then it's got remote, which is what this guy is automatically. It means you switch it between the modes with your computer. And then it's got the run mode. The 504s have that. Now, a lot of your industrial people like that because you can switch it to run mode and then do what with the key? Take it out. And then somebody can come in and do what? They can hook a computer to it. And they could upload the program, but they can't change the programs. The only problem I've seen is that all the keys are the same. So you have to guard the keys. So I like, most of these guys like this, these small hybrid PLCs, these are always in remote mode, which means you switch them between modes with the software. Everybody okay there? Then the online monitor mode, this guy here, they just called it online. So if we go online and notice it does it automatically. It goes on online, and what does that show you? That shows you what's active, right? So that's a really good troubleshooting tool, guys. I mean, if you're expecting an input, so instead of you going out to the line anymore, if you got your PLC's network, and we can network these, especially this, because this is Ethernet. So I could literally hook this up to my plant network, and I'm having problems, and I could go to that online, and I could see that sensor working or not working, right? Y'all understand that? I can see if it's false or true right there. Right? I mean,
do it in another state.
Do it in another state if you're courageous enough and you have a really good firewall and you have a lot of protection on there. Normally, if you did that, you would password protect the program, and then that way somebody that got
That's
it.
how they troubleshoot the industrial car washes.
Yes. Yeah, but you got to be real careful. If somebody breaks into that, they could
start washing cars.
Not start washing cars. They could bring something down when it's not supposed to be down, and bring something up when it's not supposed to be up, right? So you can make that thing go. So that would be fun. Yeah. So if we network them, then they could actually troubleshoot or make programs not even inside the plant, but if you open your network up to outside, but you need to really protect that, right? So all these PLCs give you the ability to password protect the PLC. We're not going to do that. Y'all don't do it. Right. I'll show y'all where y'all can do it. But don't password protect them. That means we wouldn't be able to get into it, sort of. We could kill it. We could do a factory reset on it, but we'd lose everything that's in there. So normally we write our programs offline, right? You understand? So we switch our program to offline. Everybody see how to do that? Are you okay there? And then all we have to do is download it. Now the problem if you've got one of the 504s, you're going to have to remember to take that key. If you don't have it in remote, you're going to have to remember to take that key and switch it from run to the program. Everybody okay? If you put it in the remote, it'll work just like this, but it's up to you. We already talked about how to wire these things up. By the way, every one of the labs we do, will actually do, you're going to have to generate these diagrams. How you would connect the PLC. And they're not that hard to connect. This guy right here, I could probably wire this thing up to this thing. I could probably do it in 15 minutes. Because there's not hard once you understand how it works. This is not right because they're getting the common right here. That's not true. The common is going to come from some power supply somewhere, right? So this would be, depending on what we're doing. So that right there would be what? So my inputs would be sourcing or syncing. Well, I should have made it. My input devices, so you're right, my inputs would be syncing. Because I've got the plus and the actual devices would be what? Sourcing. That make sense? By the way, when you look at the 504s, when wherever them are, the input modules, written right on the input module says syncing. And the output module says sourcing. That's written. So those modules, you don't have the ability to change it. This guy right here, you can change it in groups, right? You understand that? We just have them both there. And so if I'm sourcing, then what would happen? Then we'd point the power supply that way. So this means my outputs are what? Sourcing, and then this right here would be hooked up. We'd call this syncing. And unfortunately, the book just mentions that. I think it's just it's inside of a paragraph. But you're going to find out that this, in PLCs, this is important. Because especially when we use solid state sensors, and I need to show y'all some data diagrams. And this only applies to DC. It don't apply to AC. So technically AC doesn't have a polarity because it's changing what? So fast. Yeah, Alabama Power is changing 120 times a second right there. That's what you're looking at. These lights are actually flashing, by the way, 120 times a second. Which means it's on for 8.33 milliseconds. Then it does what? Then it switches polarity. So we take for granted it doesn't have that. Syncing and sourcing only comes into play when you're dealing with DC. And everything in here is DC, 24 volts. 24 volts is very safe, right? And it's a standard power for most of your solid state sensors. So what you need, if you're looking for sensors, an NPN sensor is a syncing sensor. And a PNP sensor is a sourcing sensor. So, you know, that's something you need to know, because if a sensor goes back and you got to buy one, and you buy a sourcing sensor and you got a sourcing input, then what's going to happen? It's not going to hurt anything. It's just what? It's not going to work. So if you got a sourcing sensor, it's got to hook up to a syncing input. Outputs usually motors don't care. Relays don't care. Relays don't care which way you hook them up. You know, they don't have a neutral. An AC relay don't have a neutral or hot. Even a DC relay don't have a neutral or hot. So whether you use a sourcing output or a syncing output on outputs, most outputs don't care. You got to be careful on it if you had a little DC motor, because that would determine what? The direction of it. So every one of your labs, one of the things they're going to want you to do, I think it's almost all of them, is they're going to give you this diagram right here, and you're going to have to wire the way you would want. Now out here, you do not use PLC symbols. You use the symbols for what you hook up there, right? You understand? Because this is what the electrician would use. All right. Everybody okay? Understand that? Offline mode, online mode, are we okay? So we use offline mode for what? Programming. We're not putting our PLC offline, we're putting our application offline. So our application is offline, right? You understand? Your PLC is in program mode to upload or download programs, right? But your application is offline if you want to do what? Write your or change your program. You go online, you have to download it and go online to be able, you go online to monitor it. Is that okay? Run mode. So when the PLC is in run mode, what's it doing? It's running the program, whether you monitor or not. I could come up here and I could disconnect that sucker from there. This sucker's in run mode. So what's it doing? It's running that last program, right? Y'all understand? I still got my stop button. I got all my inputs and everything that are still working. So once you got that thing in the run mode, you can disconnect your computer and you can take it home with you, right? And that sucker's just going to stand there and do that scan 24 hours a day, 7 days a week, right? Force. Everybody okay on forcing? This PLC is really easy. It's real easy. Siemens, you have to set up a force table. So you have to go in and say, I want to force this contact, I want to force that contact, and you have to enter everything you want to force. For Allen Bradley, you just go to that force table, and all you got to do is make sure you know the address, right? So forcing, we use that for troubleshooting. We could force inputs, which means I could verify a program runs before I actually hook it up, right? Y'all understand that? So we could actually do that. Not even have any input devices up. It's just I know what each one of those bits do, and I could force them on and on. Forcing outputs, guys, you got to really be careful on that because those are going to be running things, right? So before you force an output, you need to make sure you know exactly what the consequences that's going to be. I think I told you about the guy at US Steel that got pinched up in the top of number 8 blast furnace because they went and forced the what? The wrong contact. And they didn't lock out the bottom one. They locked out where they was working on, but they didn't lock out the bottom one. I think I told you about my number 4 galvanizer too. Place PNC and offset and create a ladder logic diagram, download the program, place it, right? We were looking at it. And we're not going to print it. This guy here gives you the ability to print your diagrams. You got to be really, really careful because there's a lot of information. And we found this out. We told it to print it, and it printed everything. Oh, I lost mine. No, you don't want to do that because that would print everything. So you go to print. No, I'll print it out sooner or later. So we printed off all the diagrams for the we got one more. Nope. I'll find out how to do that. There's one big difference with the Siemens and the Allen Bradley is that you upload it, download it into the PLC. All this stuff is not all your tags and comments are simple comments
are not downloaded.
That means if you upload a program, you're not gonna get all your tags, you're not gonna get all your symbols. Anything else? And I'll say general report, title page report, process information report, IO configuration report, channel configuration report, channel 1, channel 0, custom data monitoring report, cross-reference report, multi-point list report, continued, database report, address symbol option, instruction comment option. Okay, this is all the reports. They didn't put the ladder in there. So I'll try to figure out again how to go in and just tell it to download what you want. Because if you just tell it to download the report, it's going to download what? Everything. You'll end up with that much paper. So I showed y'all how to do symbols, right? Is everybody okay there? So how do we do symbols? We got one or two options. When we insert something into the rung, then when I come up here, so first of all, you gotta highlight the rung you want to insert it into, right? It turns red, and then you drag it down, and then notice these little X's turn green depending on where you want to put it at, right? That makes sense? And then what's the next thing it needs?
Address.
An address. Flash with on PLC. Now this is where you could set comments, right? Or you could give the symbol a name. And probably names are more important than comments. Because if your name, then instead of trying to remember the address, then all you gotta do is remember the what? The name. So if I was to call this Bill, right? And then I come down here and I wanted to put a contact down here. I'm going to come up here instead of typing the address, I'm going to type in Bill. And what did it do? It automatically put the address that I assigned to that symbol. Now, newer PLCs call these tags. They don't call them symbols. And if you make a mistake, oh, I didn't want to call that Bill, I wanted to call it Bob. And what can you do? Come down here to your address symbol table. Find Bill. Just go over here and double click on that. Call it what? Bob. Or Bob. That's good enough. And then it should have automatically did what? Yeah, changed it. Huh? Yeah, you could, but the problem we have is we use a symbol. And then we realize we put that symbol in the wrong spot. So we try to put duplicate symbols. So what you can do is you can go into that chart and delete that symbol name, and it gives you the ability to use it again. Does that make sense? What's nice about the symbol table is you can go ahead and assign all your symbols before you even start your program. And then once you assign your symbols, then you're not worried about addresses anymore. All you're doing is just typing in what?
A little bit quicker that way.
Yeah, it's a lot quicker. The symbol table, the tag table for that one over there, I think there was like, good gracious, I forgot. I'd have to look it up. So what most of the people chose to do is to go ahead and enter their tag table and assign their addresses and everything, and then from that on, they could use the same name that was on the Allen Bradley prints. So Allen Bradley, when they converted from the Siemens over to the Allen Bradleys, they already had the tag table out there. So you go up there and set up your tag table, right, you understand, or your symbol table, and then when you write your program over on to the 1200, you just type in names. It made it really, really easy. But yeah, you get an option, two ways. You know, you can do what? You can type it, you can give the symbol a name when you create it. Or you can do what, Tyler? Yeah, you can right click it and go to what? You can edit symbol, right? Right. Or you can do what? Yeah, every one of them that had that name before, not unless it's a repeat symbol. And this is where we got into problems, is people were doing symbols and then they would try to give them both the same name because they named one of them wrong, or they changed their program and try to move stuff around. And this guy's really neat. You can move stuff around. So if I didn't want this contact right here, I could do what? I can hold left mouse button and I can move it down there. I can come up here and I can highlight that. Y'all know the shortcut keys for Windows? Control C, Control V. I can come up and highlight that. So if I had this same contact in multiple lines, I can hit Control C and then I can come up here. If this works. Hit Control V. And then you can put it where you want to. So Control V, Control X. Control X does what? Cuts and paste. So you can cut and paste, right? Control V is paste. Control C is copy. So you can use those Windows shortcut keys in here. Are we okay? I know y'all ready to go. Lecture nights are real long. We're going to try to, and what we're going to try to do also is we'll show you how you can actually, we don't want you to save your programs on the computer. We'll show y'all how to access our file server too, how to actually save them on our file server. And then that way at the end of the semester I can go out and delete it in one spot instead of going down every computer. Okay, any questions? Y'all learn anything tonight?
Yep, sir.
Except that the box you broke, right?
Learn that.
It would have been fine. So I got to figure out how to fix that because that's fun to do. Okay, see y'all guys. Oh no,
Touch on that. Touch the
labs. Labs are due, right? The ones we're supposed to do. The numbering system lab.
I got these are still in.
Yeah, the gray code. Don't worry about the gray code. Where's our stapler? Oh, right there. Let me just stapler. Yes. But the test will go through this class. So I got to rewrite it because we moved it. We still got to cover the same material. So since we moved the test, we're going to have to add more material.
Don't make it too hard.
Don't make it too hard. And you got to remember, you're talking to the teacher. I have people say that to me. Is it hard? I say, not to me.
same thing. You gonna be here for a minute?
And for 15 more minutes. I think I told you.